Okay, hello everyone. Now let's get into the subject and let's make a short introduction about the fundamentals first. And we will begin with the general principles. Now, our name of our course is statics, but we are mechanical engineers, and fundamentally, as an engineer, our task is to design tools which will be used, which will simplify the life of the people, the daily life in general. And for this purpose, we are using mechanics. Mechanics is a branch of science, and it investigates the equilibrium or motion of the objects when they are subjected to a force. So, for example, now I have a ruler here. Okay, I apply a force and it's curved. So what is the force that it can withstand? This is one question, for example. Or I may need to design a motor here, an electrical motor. It has a shaft, and what will be the temperature, maximum temperature that it can run? So such kind of questions has to be answered by a mechanical engineer. Of course, there are different branches of mechanics. First one is the mechanics of rigid bodies. Okay. Yes, rigid. Now we have a new thing, rigid. So what is rigid? When an object is non-deformable, so if you apply a force on it and it doesn't deform, like what? Like, for example, this steel bar. I can consider that it is rigid, it's non-deformable, its geometry does not change. Okay, so first thing is the mechanics of rigid bodies. What else? Mechanics of deformable bodies. Now, deformable is our word here. Now, let me take this steel ruler again. You see, I apply a force and it's curved. So it deforms. So what will be the strength? What will be the maximum force that it can withstand? So this is the subject of mechanics of deformable bodies. What else? Fluid mechanics. Fluid. Okay. Now, as we see, many of the objects are solid, but maybe there are other types of materials such as liquids and gases. So they flow. For example, wind flows from one place to the other, or the water flows from one place to the other when it's subject to their force. So they are fluids, and that's the fluid mechanics mainly investigates the behavior of such materials under a force. And the last one is the quantum mechanics. We don't use it very often, but of course here the word is quantum. So what's a quanta? So basically the quantum mechanics investigates the behavior of a particle at a microscopic level. For example, the electrons. They are really tiny, they don't have the geometry, and in fact you cannot even though it has a mass, it is at a particular location in space, very tiny. We cannot measure. It's very difficult to define its geometry. So that's called a, but it has a mass, it has a velocity, certainly it has an energy, and this is called a quanta. And as a result, the branch of the mechanics that investigates behavior of such kind of a tiny particles is called, or very fast in fact also, they move almost very close to the speed of light, and it's called quantum mechanics. So these are the branches of mechanics. Okay, now our name of our course is statics. Certainly mechanics of rigid bodies can be divided into two groups. One is the statics and the other one is the dynamics. Now, statics investigates when the object is in equilibrium, when the forces acting on an object is in equilibrium, so it doesn't have any acceleration. How about the dynamics? It moves under a force. If the force is not equilibrated, certainly the object will move from one place to another, and under that condition we want to predict its behavior. So that is the subject of the dynamics. Again, okay, now the point is this: we are designing tools for people, and we are living in the universe, on the earth. In fact, first thing that we do is we define the distances, because we want to analyze the behavior of an object, and first thing that we do is we need to define its position in space. So certainly we define the location of particular object by 3 coordinates in general, 3 points, sorry, not 3 coordinates but 3 points. So if you are living in a room, sitting on a chair, and you say that, okay, there are tiles maybe around you, and you say that there is another object, and you say that, okay, this object is 3 tiles in front of me and 5 tiles on my right side and 10 tiles towards the ceiling. Then you give a coordinate of the object. Certainly there is another parameter that we use, time. Well, according to the Einstein, time is the ticks of a clock. But certainly we define it like this: it is the moment that an event happens. Let me take out my ugly face. Yes, it is the moment that an event or events happen. This is what the time is. Okay. Now, as we have seen, I push this ruler, okay, and it deforms. And I say that I apply a force on it. So what's force? Force is the attraction or repulsion which is applied by a body to another. So with my right hand, I apply something. Certainly I feel something because I push it. So this is the force. This is what I define as a force, but the measure is of course the something else, and we will see how we measure the force. Now I apply a force, and certainly this ruler applies me a force. Okay, now so these are the parameters. So as a result, I have the position of an object in space given by 3 coordinates, and then I have the time. and these are called independent variables or parameters generally. And I have a force. We made the definition for the force, and let's look at the titles on under the statics. Now statics can be divided into three subtitles: statics of particles, statics of bodies, and statics of deformable bodies. Now within this course we are going to study only two of these: statics of particles and statics of rigid bodies. Now statics of deformable bodies is the subject of strength of materials course or mechanics of materials course. Okay, so now we have made the definition. We haven't made the, we talk about it, but we will make it in detail, the definition of the rigid body and particle. So we have two new thing, which is a particle, what is a particle and what is a rigid body. Okay, so if an object can be represented by a single geometric point in space, then that is, of course, it should have a mass. I forgot to tell it. We call it particle. For example, atom in a room can be considered as particle, single atom. Or let's say a steel ball in a very large room or in a conference hall can be considered as a particle. Earth in the universe, because the size of the universe is very big compared to the Earth, and Earth is like a point, then we can consider the Earth as a particle. Okay, now rigid body. Now let's think that an object is made of infinite number of particles connected to each other. Okay, so each particle is connected to each other by, let's say, that artificial springs, invisible springs. And I want to deform it. I apply a force. Certainly it tends to deform, but for the moment, let's assume that the springs are highly stiff. Therefore, the object cannot deform. As a result, the relative position of these small particles cannot change. So this type of object is called rigid body. So let's make the definition. If an object is made of many particles and distances between the particles do not change, that object is called rigid body. That's the definition of a rigid body. Now we are analyzing the we want to analyze the behavior of the objects, and Isaac Newton, all of us knows, I think, Isaac Newton devised three fundamental laws which we have been using for 350 years, more than 350, sorry, and still using these laws for designing the tools for daily life, for high-tech application. So this basically shows that how the science progresses. Science get into our daily life in a very, very slow manner, so slowly, very slowly. Okay. So the first law of Isaac Newton tells us, first law of motion. If the net force acting on a particle is zero, so I have different forces acting on an object, for example this one. If the net force is zero, particle or object does not change its state. If it is not moving, it will keep its position. It will continue to stay there. But if it is moving, it will continue to move with a constant velocity. So this is what it means. Okay. Now, second law, the famous one, a particle accelerates in the direction of net force acting on it. So we know this rule as force is equal to mass times acceleration. F is equal to m multiplied by a. So this is the second law of motion. Of course, when you apply a force to an object, for example this one, if I push it, it will move in this direction because there is nothing to resist. But if I put my hand here, left hand, of course it cannot move because the forces are equilibrated. Now, when the forces are not equilibrated, it will move. This is what the second law is. Now, the third law. If two bodies is in contact, they apply each other a force which has a same magnitude but opposite direction. So, okay. Now, again, I take my ruler. Now, I have an eraser and I put it here. So what will be the force between the eraser and the ruler? Okay, they apply each other a force because this has a weight, and or let me take the eraser. I push this ruler. I apply a force in it. Certainly this ruler applies a force on my finger, and they have the same magnitude but will have the opposite direction because the ruler pushes my hand to the upwards, and my finger pushes the ruler to downward direction. Okay. Now, Newton's law of attraction. Isaac Newton has another law. Two bodies apply a force to each other according to the third law, it says. So what it means? Now, just think that Earth and Moon. Okay. Now, Moon is turning around the Earth. There is a certain distance between them. Let's say that this distance is r, and the mass of the Earth is capital M, and let's say that the mass of the Moon is small m. In fact, Moon attracts Earth and applies a force of F2 on the Earth, and Earth applies a force of F1 and attracts the Moon towards it. And the magnitude of these forces are equal. Now the expression for this is G times multiplication of the masses, so capital M multiplied by the small m divided by the r square. This is what Isaac Newton found when after analyzing the many celestial objects, and G is a universal constant. So it is 66.73 10 to the power minus 12 meter cube divided by kilogram second square. Okay, so this is the law of attraction. Now we have the mass. Mass is universal and it cannot change, but certainly there is another thing, weight. Now, for an engineer, weight is the force acting on an object due to the gravity. And the thing is this, gravity may change. Depends, and it depends on whether you live on the Earth, or you live on the Mars, or you live on the Moon, or on the Sun. Now let's write the law of attraction between two objects. Just assume that you are living on the Earth or any celestial object, and let's assume that this celestial object has a mass of me and has a radius of r, and you live on this capital R. Certainly you have the mass small m, and this celestial object will attract you according to the law of attraction, and as a result the force applied to you is g multiplied by the mass of the celestial object, it is Earth in our case, multiplied by our mass, divided by the square of the radius of the celestial object. In our case it is the radius of the Earth, and this is equal to weight. This is what the weight is. And we say that weight is equal to mass times gravitational acceleration. Therefore, we can easily calculate the gravitational acceleration, which is denoted by g. G is equal to universal constant of attraction multiplied by mass of the celestial object divided by square of the radius of the celestial object. And in fact, on Earth, g is equal to 9.81 meter per second square. Sorry, this is not second, this is square. Huh? Let's write it. That's bad. So this is what the gravitational acceleration. Okay, this is a very short introduction about fundamental definitions and what we are going to see within the course of statics.